My name is Professor Prof Orata. We are continuing with our thermodynamic lectures. Today we look at measurement of enthalpy. Measurement of enthalpy. And we are going to use the flow calorimeter to measure the enthalpy values. Using flow calorimeter. Now, in the flow calorimeter, we are anchoring our measurements on one fundamental equation which we derived from first law for steady-state flow processes, first law of thermodynamics for steady-state flow processes in one of the earlier lectures which we have. And that law, from first law of thermodynamics for steady-state flow processes, we saw that dH plus dc squared over 2 plus g dz is equals to dq plus dw. And we said that can be plus or minus. In earlier lectures, we said that's just a question of notation, what you have chosen notation to be. If your minus W is work done by the system of the surroundings, or if plus W work done the system by the system of the surroundings, that's one's choice, only that you use it consistently. So this represented terms for kinetic energy, that represented term for potential energy. And since we are doing these things under adiabatic conditions, under adiabatic conditions and no work done, but we are only monitoring the work which is transmitted into or out of the system, we are saying that we are assuming that no work is done. For example, shaft work, we are saying there's no shaft work in that particular process, so that we are left only with the heat measurements within that system. So we are saying that we have dH then will be simply equal to dq. I repeat, we are assuming that potential energy is zero or insignificant. We are assuming there will be no changes in elevation, so that will also be zero. And we are assuming that there's no work. Those are the assumptions which we are making in our efforts to determine or measure the enthalpy values. Now, let us look at the flow calorimeter, what's the schematic for it. So in a flow calorimeter, we'll have a constant temperature bath, and in this constant temperature bath, we will have a filament. So let's call this a constant temperature bath. In other words, the fluid which is flowing in this coil, the liquid, which in this particular case will be water, flowing in this coil, we make sure that its temperature is kept constant. So what we can do is have some ice, mixtures with water. To keep the temperature, ice-water mixtures, ice plus water, to keep the temperature at 0 degrees centigrade. So that the water which is flowing in this coil, this is just a coil, tubing, coil. The water flowing in that coil, the temperature is maintained at 0 degrees. And then it flows to the electrical heater. So this is an electric resistance. That's the EMF. That's an electric Then it will move into the unit or system where we are able to determine its pressure and temperature. So let's say that's a thermometer, and that's a pressure gauge. So for measuring pressure, this is for measuring temperature. Of course, we have a valve here. Valve is a release gadget so that you can close it or open it. And then of course we have the discharge. So this is a schematic of our flow calorimeter. This is a schematic of our flow calorimeter. So we have this, like you have said, a constant temperature bath to make sure that the temperature of the water which leaves this unit going to the electrical resistance there is at 0 degrees centigrade. And we said you can effect that by having ice mixed with water, and that will, and in the process, even make it more effective. You can have many coilings, much more coilings to just increase the surface area of this particular process. Then we have the electrical resistance, and we have the unit where we measure the temperature and pressure, and of course the discharge valve. Now, at the heart of this discussion, we have said that when heat is transferred under constant pressure conditions, then that change, we are measuring the change in enthalpy. Remember always heat transferred, that is Q, heat transferred under constant pressure is the enthalpy change. And this you have seen now severally, because it's very important. That's dH is equals to dQp. And like we have always said, this is a thermochemical observable, that's a thermodynamic state function. So the link between them is very fundamental in thermochemistry. Now, the link between a thermochemical observable, thermodynamic state function is fundamental in thermochemistry, which is the basis of some of these particular measurements which we are making. Now, we are saying that we have already our system here which we have configured to be able to determine this, because we have said in this system we make sure that the flow of the flow velocity of this liquid is very small, so that we ignore kinetic energy. And we are also assuming that there's no change in the elevation of this particular system, so that the potential energy is assumed to be 0. And we are also assuming there's no work done. There's no work done. We have talked of work being done, sort of flow of fluids, like in the steam plants. We saw the turbine doing work because of fluid being pumped into that particular system. And so forth. Here we are saying there's no work done, so that we are left with this equation here where dH is equals to dQp. And we also want to restrict ourselves so that there's no heat which is coming externally, so that the heat which is involved is internal heat within that particular system. Now, when we are dealing with this system, the water will be allowed to flow into the electrical resistance system there, which we have there. And what are we talking about when we talk of electrical resistance? The resistance in this context is basically the equivalent of friction. The resistance here is the friction in the electrical unit. For example, you have that coil, it resists the flow and the flow of current, and heat is generated. So this resistance is just the equivalent of friction, resulting in mechanical work being lost as heat. In the same way, that resistance results in electrical energy being lost as heat. Very important for us to note that resistance. That resistance there, I need to write that down. That resistance we are seeing there, putting in quotes, is the equivalent of friction. And the same way, I repeat, friction causes mechanical energy to be lost as heat, is the same way electrical resistance causes electrical energy be lost as heat. Very important for us to note that. And so that's very important. Then we need to know a few things. When we talked in our earlier lectures about, for example, the specific steam consumption. We talked about of consumption of steam per kilowatt hour, And we had mentioned there that kilowatt hour, we are looking at this is watt, that is power, and that is time. Gives you energy. Remember that? And so, in the same way, the electrical energy is normally given as electrical energy is IVT, current times time and potential, IVT. So we need to remember those kind of things. And remember that resistance is given by Ohm's law. Resistance, electrical resistance is given by Ohm's law. Remember, electrical resistance is given as I is equals to IR. That is Ohm's law. So in this system, as the voltage is applied, then the current flows. There is always a resistance. There's a resistance. So it's like how much energy do you use to push those electrons through? That how much energy do you use to push those electrons through so that current is generated. So that electrical resistance, once again I repeat, is like friction. It's like friction in the electrical system where we have the electrical energy is dissipated or lost as heat or thermal energy. Very important for us to note a few of those things. And we know that when you look at that electrical energy, which we have said there, electrical energy E, remember that is potential in volts, that is current in amperes, and that is resistance in ohms, which we normally denote as that, in ohms. So when you're talking of electrical energy, we are saying that is IVT. And what is V? V is potential, is IR. So it's I times IRT, which is I squared RT. Some of those quantities are very, very important for you to know. So that the key thing which I want you to know here is that the electrical resistance, think of it as friction in electrical flow, electric flow, and this is where we have the conversion of electric energy into heat. That's what I want to, that's the gist of that particular discussion. Now, once we have done that, we are going to be able to measure now as the water flows here. In this section, let's call it section A, and let's call this section B. So what are we having here? We are having water flows. It is heated. We measure the temperature and the pressure. Measure the temperature and the pressure. And remember that the heat which is generated is the same as the enthalpy change, because we have said dH is equals to dQp. And so what is this quantity when you integrate? When you integrate this quantity dH, we get, and integrate dQ, we simply get delta H, which is H position B, section B, and or state point B, minus H at state point A is equals to Q. Now, let us assume that at that temperature where we have 0 degrees centigrade, the enthalpy is 0. Let us assume that H is equals to 0, our temperature is equals to 0 degrees centigrade. We assume that. Let us assume that for simplicity, so that it means that when we have that value for enthalpy in section A, we are assuming that it is 0. So that what we are able to measure is the progression, how the enthalpy changes as heat is supplied through the system. So we are able to measure that particular enthalpy. We should be able to measure the enthalpy between point B and point A, point B and point A. So this is an empirical method of determining the enthalpy of a system. Now, if we are using some fluid other than water, then your assumption of what HA will be 0 at what particular temperature will be dependent on the kind of substance which you are using as your fluid in your system. Will depend on the kind of substance you are using in your fluid as your system. Just in summary, 1, we have used the steady state flow process equation which we derived, and that is the first law equation, which is giving us enthalpy related in relation to kinetic energy, potential energy, work, and heat. And we have said that in this particular system, we are making sure that the fluid flow is minimal, so velocity is very small, so kinetic energy is not important, and we are assuming that this system is relatively at the same level, so that we don't alter the elevation, so that doesn't affect our potential energy, and there's no work, so we have our W as 0. So what we are measuring now is the enthalpy between the two locations through the state points, that is B and A. And we are assuming at A, where the temperature is 0, the enthalpy is 0. And as repeated, that assumption will vary with the type of fluid you're using. If you're not using water, maybe it might not be appropriate for you to do that. You might assume other conditions. And then now you're able to measure from the heat transferred, of course, using those Ohm's law and using those electrical power energy equations which you have shown there, you are able to compute Q as time goes by. You are able from Q as time goes by, and that Q you relate to enthalpy. So let's stop at that particular point. We'll move on with other lectures.